Hi, and welcome to Mr. Garofalo's podcast. Today we are looking at solving quadratics by inverse operations. And this is example 4. In this question, we're told that a parabola has been graphed according to the equation y equals 1/2 x squared minus 6, and that a student named Francis believes the quadratic has zeros of negative 3.5, and positive 3.5. So let's take a look at the graph here. See the parabola. A couple of features. Uh, First, you'll notice the turning point here at 0, negative 6. And notice the constant there, negative 6. That should be something that we recognize. And we identify our zeros. There's a positive and a negative 0. And Francis's belief seems to be pretty good, because if we treat these as units of 1, let's see, 1, 2, 3, 4, it looks as though this parabola intersects the x-axis about halfway between 3 and 4. And if we go the other direction, it looks as though this intersection is about halfway between negative 3 and negative 4. So this makes sense for him to use these values as the zeros. Well, let's find out if we solve it, though, if he is actually correct. So we're asked in part A to find the zeros of the function. The equation is y equals 1/2 x squared minus 6. So remember, if we're asked to find the zeros, we need to let y equal 0. So we have 0 equals 1/2 x squared minus 6. And now we have a few options for solving this. One option would be to multiply all the terms by a certain value so we can get rid of the fraction. Another option would be to isolate the quadratic term. I'm going to isolate the quadratic term first by adding 6 to both sides. So we'd have 6 equals 1/2 x squared. And I've run out of room here, so I'm going to move this over. And I like seeing my quadratic term on the left anyway, so I'm going to rewrite it on the left side. I'll continue by multiplying both sides by 2. That'll take care of our fraction here. 1/2 times 2 would be 1. So we're left with x squared equals 12. And we could solve by taking the square root. Remember, when we're solving a quadratic, we always want to find the positive and negative root. So this would be x is equal to the positive or negative square root of 12. But we're asked to write it in simplest radical form. So we'll need to look for factors of 12, one of which is a perfect square. Those factors will be 4 and 3. So we have plus or minus the square root of 4 times the square root of 3. And the square root of 4 is, of course, 2. So the zeros are plus or minus 2 times square root of 3, or plus or minus 2 radical 3. Now, this doesn't completely assure us that Francis is wrong, because maybe the value of this expression is 3.5 or negative 3.5. However, we need to take note of this part of the expression here. Square root of 3. The square root of 3 is an irrational number. And when we multiply a rational number, like 2 or negative 2, times an irrational number, like the square root of 3, we're going to end up with another irrational number. And notice the values that Francis gave were rational numbers. So there's no possible way this expression could give us a decimal that terminates like Francis has given. Rational times irrational will equal irrational. So part B asks us, Francis was incorrect, but not too far off. How can you tell how good his estimate was? Well, we would want to know what the value of that expression is, approximately. So we would evaluate the expression 2 times the square root of 3 and 2 times, negative 2, excuse me, times the square root of 3. And you find, if you place these in your calculator, that the value is approximately, the symbol means approximately, 3.464. And there are some other values here after. And then this is about negative 3.464. So he was, in fact, pretty close. 3.5 and negative 3.5. Right, today's podcast will have some bonus action to it. We're going to look at your homework, and specifically part D of question number 3. And here we're asked to solve a quadratic and write the answers in simplest radical form. So as I mentioned in class, when you encounter these types of equations where you see a binomial squared, this is the part of the equation you should be focusing on isolating. So as we start to use our inverse operations or properties of equality, ultimately we would like this to be isolated. That's going to give us a perfect square trinomial, and extracting the square root of that will be beneficial to solving this. So I'm going to start here by subtracting 37. And we get 5 times x plus 2 squared equals 450. I don't want that coefficient of 5 here, so we're going to go ahead and divide by 5 on both sides. Now remember, this is an entire single expression right here. This is a single term. 5 times x plus 2 squared is a single term, so I don't need to divide x plus 2 by 5. Simply just divide 5 by 5. So we end up with x plus 2 squared is equal to 90. 5 into 450. Now, 90 is not a perfect square. So unfortunately, it will come out to be irrational. We'll have to work through the simplest radical form process. But this is some good news over here. X plus 2 squared is a perfect square. Its square root is x plus 2. Remember to extract both roots when taking the square root of the right side here. So we end up with x plus 2 is equal to plus or minus square root of 90. Unfortunately, this is not in simplest radical form. So we have to go through our perfect square factors. Why don't you take a moment and try and figure out the factors. Pause the video and figure out the factors that will work here. Okay, did you use 9 and 10? If you did, good job. So we have the following equation, x plus 2 is equal to plus or minus 3 radical 10. We're not solved for x just yet. We need to subtract 2 from both sides. So our final result will look like this. Negative 2 plus or minus 3 radical 10. Certainly not a pretty solution set. Okay? This will be in irrational zeros, and you can go ahead and find the value of them by putting them into your calculator. Hopefully this was a helpful podcast. Should anything else arise, feel free to email me, and I'll see you in class.